All right, in this video, I'm going to talk about sine waves in the time domain. I have the sine wave and the cosine wave both here, but again, I'm just going to kind of focus on the sine wave. Maybe I could even make like a box here, and wonder if I could like make a shape that's like filled in. It's okay. I was going to try and like blot this out, but it's whatever. It's fine. So basically, what we've been talking about up to this point, we kind of saw a sine wave over here that was just in terms of t. That's not really going to work out for us, because if I plug in the sine of anything, again, this is the sine function assumes something's moving in a circle, right? And so if I plug in some time value here, let's say I plug in 8, and I'm just like, oh, I just want the sine of 8 seconds. All that the sine function knows is that something's moving in a circle, and all it knows is that if I'm in radians, I'm talking about 8 radians here, which would be, 8 times my radius going around a circle. It has nothing to do with time. And if I plug in 8 and I'm in degrees mode, it thinks I'm talking about 8 degrees, right? So in either case, it has no idea that I'm talking about time, because the sine function is, it's not made for time. It's made for radians and it's made for degrees. It's made to describe motion in a circle. And there's no time dependency in a circle, right? The circle is just described by, here we are. The circle is described by one of two things. It's either described by radians, angles in radians, or angles in degrees. And so we need a way of converting our time values into radian or degrees, right? So that we can actually plug that time value in, get the associated sine value, and then correlate that with our time value somehow. And that's what we're going to try and do here with this omega. Okay, so omega is what's called angular frequency. Let me write that out. Angular frequency. And it has units of radians per second. And you will notice that we're actually multiplying omega by t inside the argument of our sine function. Actually, don't worry about Vm and don't worry about phi for now. Let's just say that we're looking at this v of t. This will be t. And let's just say that my function v of t is the sine of omega t. Okay? So my angular frequency is radians per second. Well, how do I get radians per second? Omega is actually also equal to 2 pi times my regular frequency in hertz, or in cycles per second. And I can see that if I take frequency f, which is in cycles per second, right? And I take that and I multiply it by 2 pi radians per cycle, I cancel my cycles, and I'm left with rate 2 pi times f radians per second, which is exactly what omega is. Omega is 2 pi times f, and its units are radians per second, okay? And so what it's basically telling me, if I plug in my f here, is if I have a frequency of 100 hertz, let's say, or 100 cycles per second, then I need to take 100 multiplied by 2 pi, which would be 200 pi, right? That's how many radians I would be going around the circle in 1 second, right? Which is a lot, right? That's very fast. That means I would be going around the circle 100 times in a second. So I'm drawing this for basically no reason, but I'd basically be going around 100 times in 1 second. That's what 100 hertz means. But to convert that to angular frequency, we need to multiply by 2 pi, because we need to get it into radians per second. Okay, so what does this have to do with time? What this has to do with time is, let me kind of seep over into my cosine side here, but I'm still talking about the sine wave. Omega is equal to 2 pi f, and we know that f is equal to 1 over t, my big T, which is my period, right? How long one single cycle takes. So if I rewrite this, I can write omega t is equal to 2 pi times f, which is 1 over t, times t. Or I can say omega t is equal to big T over t times 2 pi. Okay, so now when I plug in my period here, and then I insert a time value, I can actually just plug in a time value, and now I'm scaling by 2 pi because that's what I need to do for angular frequency. And any time value that I plug in, my sine function will actually spit out the correct value, because I have now turned my omega into omega times t, which I've made it dependent upon time. Where this fraction here, the fraction of the period, is going to give me some fraction of a cycle, because one cycle we know is 2 pi radians. And so this is how we actually take the time domain, or sorry, take the sine function and make it time dependent. We have to scale it by the angular frequency omega, okay? So for example, let's say that I have a frequency of 100 hertz, like I said I had. And let's say I want to know what is the value of my V, V of t at time t equals 1 millisecond. Well, I would go ahead and say V of 1 millisecond is equal to sine of omega t, which would be 2 pi times f, which is 100, times t, which is 1 millisecond. I would go ahead and I'd throw that in my calculator. Make sure my calculator is in radians, of course, because I'm looking at radians. And so let me just do that. 2 pi times 100 times 0.001. And now I'm going to take the sine of that value. And I get 0.5877. And so that would be the height of my sine wave. Be like right about here. Let's just say 0.587 at 1 millisecond, okay? And so that's how we convert. That's basically the purpose of this omega t in the argument of my sine function. It's to take time values and to actually make them suitable for a sine function, which only cares about radians, because we're talking about things that are moving in a circle, but we want to correlate this with time values in real circuits and in real systems, okay? So, I could plug in another value. I could plug something in like, let's say 1.1 millisecond, and I should see something that's a little bit further along. Actually, it really depends on the period here, which, let's see what the period is. It's going to be 1 over 100. It's going to be 10 milliseconds. Yeah, so if I plug in, 2 milliseconds, or let's just do 1.1 milliseconds just to prove that it's going to be larger. V of 1.1 milliseconds is going to be sine of 2 pi times 100 times 1.1 milliseconds. I plug this into my calculator. 2 pi times 100 times 1.1 milliseconds, and I get 0.63, which if I were to come in here, I basically only moved over to 1.1 milliseconds, which would be right next to it, and my y value has increased to a value of 0.637, okay? So that's what we're doing here. Of course, this is also 1.1 millisecond, just to keep everything straight. I'm going to go ahead and end this video. Hopefully this makes sense to everybody. If it doesn't, please feel free to ask questions, but basically just wanted to show, why do I need to multiply by omega? It's so that I can take time values and then use my sine function to actually get the value associated with something swinging in a circle, but now dependent upon time, specifically dependent upon my frequency, because my frequency tells me how many rotations is that vector that I'm talking about. Is how many times is that going to traverse the full circle in 1 second? In this case, it would be 100 times. And so we need to scale that 100 by 2 pi, and then we can insert our time value. Okay, going to go ahead and end this video here.